Hello. This paper presents a robust lane marking extraction algorithm for self-driving vehicles. The authors of this paper are Tesfamichael Gedahan, Dr. Ali Karamadini and Dr. Leila Hashemi Beni from North Carolina A&T State University, and Dr. Priyan Mutilaj from General Motors. Here is the outline of this presentation. First, I will talk about the motivation behind this work, followed by a brief introduction to lane detection. Then, I will discuss some of the challenging lane detection problems that several researchers have been trying to solve. After that, I will talk about the solution we propose to improve lane detection accuracy under those challenging conditions. Finally, I will show you the results of the proposed solution, and I will finish the presentation with the conclusion. This research is motivated by the fact that autonomous driving would address safety concerns of manual driving all around the world. According to the 2017 report from the International Road Traffic and Accident Database or IRTAD and World Health Organization or WHO, about 1.2 to 1.3 million people die every year on the world's roads, and around 50 million people get severe injuries because of traffic accidents. For example, the U.S. Department of Transportation report shows that about 37,133 were killed by traffic accidents in the United States. The reports also show that most of the accidents are caused by the driver of the vehicle. To reduce road casualties and improve vehicle safety, advanced driver assistance systems or ADAS, such as lane departure warning and lane keeping assistance, have been introduced in vehicles. The study by the European Road Safety Observatory shows that the introduction of ADAS to vehicles has improved road safety and reduced road crashes significantly. Therefore, in the near future, autonomous vehicles are expected to improve road safety, increase mobility and reduce overall transportation costs. Lane detection will play a significant role to this venture by enhancing the vehicle's perception and situational awareness and thus improve the safety of the autonomous vehicle. Before discussing our proposed lane detection approach, let's briefly review the current state and the future role of lane detection. Lane detection is one of the key building blocks of semi-autonomous vehicles. Unlike the ADAS, which uses lane detection system to warn the driver of the vehicle, semi-autonomous vehicles are already using the lane detection system integrated with the vehicle steering and speed control systems. The Cadillac CT6 from General Motors and the Tesla Model S or X are very good examples of semi-autonomous vehicles. Therefore, the future autonomous vehicles will rely on lane detection to control the steering system of the vehicle regardless of various road conditions. The problem is that detecting lanes is not that easy. So, what are the challenges of lane detection? Lane detection is a well-defined problem. However, because of the various challenges that exist on the road, the problem still remains challenging. Some of the notable challenges are invisible lane markings due to aging and lack of maintenance, road texture variations which could be asphalt or cement roads, shadows from trees and bridges, lighting variations like day or night, and interference from other traffic signs on the roads, especially on urban roads. Due to those challenges and their variants, extracting the lane markings to identify the lane is a big issue. In an attempt to handle the problem, literature shows that various techniques have been proposed. Canny edge detector with Hough line transform is the popular technique to extract the lane line features. Canny edge detector is a famous method to find the edges in an image. And Hough transform is used to extract the lines and line segments in the image. However, the Canny-Hough technique is not that effective for roads with faded lane markings, old roads with repair marks, and curved lanes. Recognizing the limitations of Canny-Hough technique, we propose an enhanced lane marking extraction solution that can perform very well under the challenging road conditions. Our proposed solution depends on the Gabor filtering and an inference mechanism that uses lane attributes. Here is the proposed solution. The block diagram representation of the proposed solution is as shown. Basically, the system takes one image frame at a time and applies some image pre-processing routine to enhance lane features. Then, the image is transformed to bird's-eye view to eliminate the perspective view. This step allows us to measure lane dimensions like lane width, length etc. Then, a lane marking extraction algorithm, which is the contribution of this paper, is applied to extract the lane markings. Finally, curve fitting is used to generate smooth curves that represent the lane boundaries. The details of the blocks are presented next. Here, the first block is basically the image source. It could be live stream from camera or a video file or collection of images in a file. The input image is expected to be in RGB color format. The pre-processing block essentially performs two important operations. First, it converts the RGB image to grayscale image. In this conversion, the white lane paintings are preserved. In order to capture the yellow lane painting, it also converts the RGB image to YCRCB color space. In this color space, the CR channel preserves the yellow lane paintings better than the other channels. Finally, the grayscale image is fused with the CR channel. The output of this block is an enhanced lane marking. Then we have a bird's eye view image. In this block, the perspective view of the image is transformed to the top view or bird's eye view using the transformation called inverse perspective mapping (IPM). This transformation is done by selecting 4 points in the perspective view and matching 4 points in the bird's eye view image. These points should be selected in such a way that the lane lines appear parallel in the bird's eye view image. This can be accomplished by a few try and error steps. Based on these points, the transformation matrix containing rotation and translation effects can be calculated. Using the transformation matrix, all the pixels can be mapped to the new image. The bird's eye image is useful to directly measure lane dimensions in addition to curvature measurements. The next block is the lane marking extraction. The contribution of our work lies in this block. To extract the lane markings, we adopted a Gabor filtering technique that is more popular in texture segmentation area. The Gabor filtering operation enhances the intensity of the lane paintings and suppresses the surrounding regions of the lane paints. The inference mechanism takes filtered image as input and separates the lane markings from noise and other similar features based on lane attributes. Gabor filter is a Gaussian modulated sinusoid function with many tuning parameters like the standard deviation, wavelength, orientation angle, and phase offset as shown in the equation. Using these parameters, the filter can be adjusted or fine-tuned. In our implementation, we used vertical orientation with kernel size of 7 by 3, although a square kernel like 7 by 7 is also possible. The image at the bottom shows the filtered image using the Gabor kernel of size 7 by 3. The intensity plot of the row indicated by the yellow line is shown on the right figure. The 3D plot of a section of the Gabor filtered image is also shown. These plots are to illustrate the effect of the Gabor filtering on the lane markings. In other words, Gabor filtering enhances intensity of pixels on the lane markings and suppresses pixels around the lane markings. This effect creates a pattern as shown in the figures. The proposed solution or the inference system makes use of this pattern created by the Gabor filter. The inference mechanism is briefly described by 3 main steps. First, it checks lane marking thickness if it is in the acceptable range. Second, it calculates the average intensity of the lane markings with valid thickness. The assumption here is that the lane marking appears brighter than the background most of the time. Third, it calculates the lane width if it is in the defined range. Here is the lane marking extraction algorithm which implements the inference mechanism discussed earlier. As you can see, the first block collects the coordinates of pixels whose intensities are 0 or close to 0. The second block computes thickness between subsequent pixels' coordinates and compares it with a defined lane marking thickness threshold. The accepted pixel coordinates will be stored in a new list. The third block computes the average intensity of sequence of pixels forming valid lane marking thickness checked by previous stage. In the last stage, the width of the lane marking is estimated and compared to a threshold. All the pixels' coordinates that pass the 4 stages are considered part of the lane markings and are stored in a new list. So far, we collected all the pixels' coordinates that are part of the lane markings. The final stage is curve fitting based on the collected coordinates. At this stage, a third-order Bezier curve fitting is implemented to generate representative lane boundaries. In order to use a Bezier curve, first all the 4 control points need to be calculated. To do that, output pixels coordinates from the inference system are separated into 2 groups, each representing the left and right lane boundaries. In this paper, only a single lane or ego lane is considered, although the proposed solution could be extended for multiple lanes. Left and right lane boundary pixel coordinates are further divided into 4 sections and average coordinates are calculated per section as shown in the figure below. Then, using the equation shown above, the Bezier curve points can be generated and plotted as shown in the figure below. To experimentally test and validate the proposed solution, we used two common datasets, one is from Caltech and the other is from Udacity. We also implemented the Canny Hough technique so that we can compare it with the proposed solution. About 2,000 image frames are manually labeled and are used as ground truth data. Pixel-level accuracy evaluation method is also employed. This performance evaluation method simply calculates the horizontal distance between the ground truth lane marking pixel position and the calculated pixel position by our system. The position difference is treated as error. If the error is in the defined threshold, the calculated pixel position is counted as correct detection or true positive (TP). Otherwise, calculated position is considered incorrect or false negative (FN). In addition, if the calculated pixel position does not have a match in the ground truth, then the result is considered false positive (FP). Using this evaluation method, for the Caltech dataset the proposed solution performed with 96% accuracy while the Canny Hough method performed at 94.8% accuracy level. Our solution performed slightly better than the Canny Hough technique. In this dataset majority of the lane lines are straight, which means that the Canny Hough technique can also work well. The images show the detection results from our algorithm for some of the frames in the Caltech dataset. In the Udacity dataset, however, which contains curved lanes, texture changes, some shadows and old lane markings with repair marks on the road, the proposed solution performed at 99% accuracy while the alternative method worked at 71% accuracy level. This shows how much enhancement our algorithm provided over the commonly used Canny Hough approach. The figure shows the result of our algorithm for some of the frames from the Udacity dataset. This figure shows the comparison between the Canny Hough approach and the proposed method. The images contain old lane paintings and repair marks. As a consequence, the Canny Hough technique easily lost its accuracy because of the false edges generated by the repair marks, whereas our algorithm rejected most of the false edges using lane attributes as measure. This is a video demonstration to show you how the proposed solution performs well in terms of detection accuracy 99% and speed of operation up to 25 frames per second using Core i7 Intel processor with 8 GB of RAM running at 3.6 GHz. To conclude this presentation, we would like to highlight the following remarks. We proposed a robust lane marking extraction algorithm. The proposed solution uses the bird's eye view image to easily estimate or calculate lane parameters such as lane width and lane marking thickness. The essential elements of the proposed algorithm are the Gabor filtering for lane marking feature enhancement and the inference system for lane marking extraction. Experimental results showed how robust the proposed algorithm is compared to the Canny Hough technique, especially when there are challenging scenes on the road like curved lanes, road texture changes, some shadows and worn-out lane paintings. Before we finish the presentation, the authors would like to acknowledge the support from SAE International, General Motors, and Air Force Research Lab, as well as the technical support from researchers at the Access Lab. For any questions regarding this work, please feel free to send it to the authors via email. Thank you.